will studying session on basics of data structures and algorithms. We can go step by step and this can make a that video. Let's get started. Oh, oh. Not further. So let's get started. Um, so let's start. We're going complexity first. So if someone gives us a problem that says check if a value exists in a collection of numbers and you need it to be honest. So will you store those numbers in a list or set? I think I'll store it in a set because it has key value pairs and when I need to retrieve a value, I think that will make it easier. But also there is fast open lookup in a set. Sets are not actually key value pairs. Dictionaries is key value pairs. Set is just value but with no duplicates. So, for example, set could be 1, 2, 3 with O1 lookup in the curly brackets. Dictionary consists of key value pair where similar to JSON format. Uh, so, suppose in bracket you have A and then the value is 1. In bracket B, the value is 2. And what is this list is ordered value or list, but duplicates are fine. So it could be 1, 2, 2, 3. So 2 is repeated twice. So both set and dictionary use hashing under the operation, which is why both have open but a set stores just only values, whereas dictionary maps keys to the value pairs. So when I want to check the existence of an element, I will use. However, if I want something to store or something associated with the value, with each value, I'll use a dictionary. So this was just a basic question. Now let's talk about primitive types. So what is a primitive type? base level, everything in a computer is just bits, like zeros and ones and memory. A primitive type is how your programming language interprets those bits. So in languages like C, Java, we have int, character, float, double. But Python abstracts much of this away. So we have like few primitive types like int, char, double. Integers have arbitrary precision. Key operations include addition, subtraction, multiplication, division, modulo, and power. Floats are 64-bit decimal numbers, which has dot in them, so 0.1, 0.3. Booleans are true and false. So in Python, bool is actually a subclass of int. So true is equal to 1 and false equal to 0. And then we have the bit operators, which is AND or XOR, NOT, left shift, right shift. So A and B will evaluate to true only if both bits are 1, because 1 and 1 is 1. Uh, and then A or B will evaluate the 1 if either of those is 1. A nice way to remember that I used was and is something like multiplication and over is equal to addition. So that's I like that was a trick from myself. And then there is also XOR. So A XOR B is one only if the bits are different. Lot of A talks about flipping the bits. So if it's zero, then we'll flip it to one. And then left shift is multiply by two, and right shift is divide by two. So yeah, this is one concept. And then in machine learning and AI, when we use one hot encoding, we are really doing binary representation because we are converting every time 0 and 1. So we store a Boolean mask over NumPy array. We are doing bitwise operations at scale. Okay, so suppose if we have a problem statement now, we want if we have a number which is in binary, for example 1011, and we are asked to count the number of 1 bits and convert the binary to a decimal. So my number is 011. Step 1 will be counting the number of ones, which is 3 plus 111, right? So it's the decimal number is 3. So how do we convert a decimal number into binary? So the decimals are the numbers which we use daily, like 1, 2, 3, 4. It is of base 10. So every digit position represents a power of 10. If we have the number 342, it means 3 multiplied by 100 plus 4 multiplied by this 2. So basically 3 into 10 to the power 2 plus 4 into 10 to the power 1 plus 2 into 10 to the power 0 is of base 10. What about binary? Binary is base 2. Same idea, but every position is a power of 2. So 2 cube is 8, 2 square is 4, 2 to the power 1 is 2, 2 to the power 0 is 1. So to represent 11 in binary, we should ask which powers of 2 will give me 11 if I add both of them. So let's see. I know 2 to the power 0 is 1, 2 to the power 1 is 2, to the power 2 is 4, 2 to the power 3 is 8. I know 8 plus 2 gives me 8 plus 2 gives me 10, but I want 11, so I can add one more 1. So I know a combination of 8 to 8 plus 2 plus 11 will give me 11. Sorry, 8 plus 2 plus 1 will give me 11. So number becomes 11 in binary becomes 1011 and it has 3 1 bits. Now we can try, and now I know that it has 3 1 bits. That's how it's 3. Other is divide by 2 method. How does a computer think about it? So let's say I want the target number to be 11, right? So I'll do 11 by 2. It is 11 by 2. 5 question and then remainder is 1. So 1 goes to the rightmost bit. And I'll do 5 divided by 2. Then the remainder is 1. And then 2 divided by 2. The remainder is 0. And finally 1 divided by 2 is 0 but remainder 1. So now I read remainders from bottom to top. So it becomes 1, 0, 1, 1. So what is the pattern here? We keep dividing by 2 and we keep collecting the remainders. The remainder will always be 0 or 1. And that is our mode. How will we code this in Python? If we are given if we are given the string 1011 in commas in Python, how will we count the number of ones in the string? So I can do a one liner that 1011 dot count function. Count and then count 1. So in that string, count the number of ones. It will return 3. So Python strings have a built-in dot count method that counts the occurrences of substring. Another method is the explicit loops, which is we can start with total equal to 0 for bit in 1011. If bit is 1, then increment total equal to total plus 1. So to convert a number, decimal number to its binary string, um, we can use bin function. Bin of 11 gives 0 e 1011, and to count number of ones in string, we can use the count function. Mm, yeah, string. solve the problem. How many bits? Let's think about time and space complexity. How many bits does it take to represent the number n in binary? Think about it this way: 11 needs 4 bits because it's 1011, right? Similarly, 255 needs 8 bits, 1023 needs 10 bits. So the number of bits grows as what? It's exponential. Like, so answer is log n. Every time n doubles, we add one more bit. So binary creates a string of n O log n in space. Count if one scans that string, so we can time. So we have O log n time and O log n space. But there is a more better version to count with home in space. That is called bit manipulation. So bit valuation is using AND operation. And minus 1 always clears the lowest bit. So keep doing n equal to n and n minus 1. Do the AND operation between all the decimal numbers and count how many times until n becomes 0. So when we use bit manipulation, it is smarter than O log n solution because it only loops as many times as there are one bits, not total bits. So it will finish in one step and uses O1. So bit manipulation is more efficient. So the earlier version shows Python, but the bit manipulation version talks about and thinks about the low level programming at the hardware level as well. So think about in AI terms. In neural network, we use compression and model quantization. That is, we convert 32-bit floats to 8-bit integers. Engineers count and manipulate bit constantly. In feature hashing for ML pipelines, bit manipulation, which we just implemented, is used to measure the similarity between two binary features, and it is also called Hamming distance. So we have models output and a desired output, and we want to see the distance between them to minimize the loss or the number of positions where two binary strings differ. So then we can use feature hashing, or there are other applications in compression and quantization as well. Okay, so what did we learn? Uh, Some basic primitive types are numerics, integers, sequences, lists, dictionary, classes, instances, exceptions. All of these are objects. Um, we need to be very comfortable with bitwise operations like XOR. We need to understand how to use masks. We need to understand how to clear lower set bit. We need to use how to use cache to accelerate operations, things like that. Um, So let's solve the first problem, which is computing the parity of the world. So we want to compute the parity of the world. Okay. Share my screen. See if that's visible. Alright, I think it's visible. So, um, I'll write just 10 everything of the world. Okay, so first, what is parity? Parity is parity of the binary world is one if number of one bits is odd. One bits is even. Parity is zero. Grammarly. Okay. So parity is basically if the number of one bits is odd, parity is not. Number of one bits is zero, parity is not. So for example, if we have number 101, we can say that there are three ones, right? Three is a odd number. So I can say that parity equal to 1. Suppose if I have number 100 so there are two ones. 2 is an even number. Here parity is 0. By think of a light switch every time I see one, I will flip the switch and it will be off 0, right? So if the problem statement asks, okay, compute the parity of this character or this letter, how will we do that? So approach will be not brute force. So I can write my definition now with the single line numbers. I'll create a function definition. You can say height integration def. I know it's gonna happen again. Um, should I do this? Should I? Uh, Sublime text. Okay, I will write here only. Def. Just ignore this capital D. Parity of x. I'll write result equal to 0. Uh, while my number exists. I will look at the last bit and flip the switch if it's on. So result equal to x and which means look at the last bit, flip the switch. And then I'll do shifting. Right. Move to the next bit. Then I return result. So let's see an example maybe. So what is x and 1 doing here? We are saying that look at the rightmost bit only. And we are asking is it 0 or 1? Then this result, what is this expression doing? It's talking about XOR operation with the result. XOR means with if 1 if 0. Result toggles between 0 and return 0 100. Double words and holds parity. Then if we do this, we are seeing that the rightmost bit at the next one. So here what we are doing is we are reading the primary number digit, 5 digit, 5 digit from right to left. Clicking on that switch every time we see one. So this is one approach. So by looking at the code, what do you think is the time complexity? I think it's over. Complexity. And actually, sorry. There is also another approach. So let's talk about which to choose for the lowest set bit. Improve the performance in best and average cases. We can do X and X minus 1 operation, which will erase the lowest 100 and 100. Similar to the count example which I told you. Suppose if I have x equal to 1, 0, 0, 0, 1, 0, 3, 100. Step 1 will be erase. So it becomes 1, 0, 0, 0, 1, 0, 0, 0. So I erased all the 1 bits, like the last one, the lowest 1 bit, right? The kind of step 2 is also erase next bit, lowest bit. What is the lowest bit now? 1 0. Yeah, becomes this. And then step 3, erase. And then finally it becomes like this. So we know we erased in 3 steps, not 8, right? This is faster approach because instead of stepping through every bit and checking every bit if it is 0 or 1 and then flipping it like the first approach, we are jumping directly from one bit to the next one bit. So suppose the number has only 2 ones, we are looping just twice. It does not matter how many total bits are there. I hope this approach is okay. Let's try to code it. So I can write another function def and show parity, which takes a number of x. Initialize another alphabet. Result. This capitalizes it. Result equal to 0. And then I can do while x with the okay. While the number exists, the result is equal to 1. The result in x. This is the operation. I'm going to keep it a little ahead. It is the lowest one bit. Turn. Okay, so this is another approach, but you can refer to this example to understand it better. Then let's think about the third approach. How about the time complexity of this? think it's gonna be over k or the number of okay. Let's talk about another approach. Lookup table. Okay. So the question here we answer what if we need to compute parity of millions of numbers. The idea is to recalculate actually idea could be caching, I guess. We will recalculate and store the parity of every possible 16-bit number in a table. Not a number, it's number. Table. So we know there are only 65536 possible 16-bit numbers, right? Small enough to store. Then we split the 64-bit number into 4 16-bit numbers chunks. Look up chunks parity and XOR the results together. So what is the analogy here? Instead of solving a math problem from scratch every time, we memorize a times table, right? So we look up and not compute. So example, if our 64-bit number consists of chunk 3, then chunk 2, then chunk 1, then chunk 0, and each of this chunk is 16-bit. So this is 16-bit, this is 16-bit. This is gonna be 16-bit. And this is gonna be 16-bit. Okay. Now, after this, we will calculate the parity. So parity will be basically XORing the results together. So I'm gonna do table chunk 3 XOR table chunk 2 XOR, and then similarly chunk 2, chunk 1 and chunk 0. Look, here we are XORing all three. Then to extract each chunk, we can use right shift, which is this. This will move chunk into last 16 positions. Then bit masking and 0x mask the thing. Zeros everything else. def parity x and mask size is 16, bit mask is 0x FFFF. Not O, it's 0x FFFF. Return then XOR oh wait, where did pre-computed parity go? Return multiplied by mask size, then bit mask, then again left shift. This is gonna be so it consists of 4 steps basically. This is chunk 3, this is chunk 2, this is chunk 1, here also it should come. Yep. Chunk 3, chunk 2, chunk 1, and then chunk 0. In this case, 4 lookups, 3 XORs. Is faster than looping through all 64 bits. Okay, let's try and look at approach 4 now. Approach 4. This is the most elegant one. Uses the fact that XOR is associative. It does not matter how you group the bits, always be the same side. parity of a 64-bit number equals the parity of its left 32 bits XORed with right 32 bits. Then we do same for 32-bit and then 16 bits and then 8 bits, 4 bits, 2 bits and 1 bit. So let's see an example. X then we do the same, but here we'll change 16, 8, 4, 2, 1. So visually, if we start with 1, 1, 0, 1, 0, 1, 1, 1, right? And we make fold. It's gonna be 1, 1, 0, 1 XOR with 0, 1, 1, 1. That is gonna be 1, 0, 1, 0. We have fold 2. Then we distribute this part into 2. First we did this into half, left and right, and then this into 2. So 1, 0 XOR with 1 and 0. It's gonna be 0, 0, right? And fold 1. Maybe 0 XOR 0, 0. So parity is 0. A good analogy to think about is fold a piece of paper in half repeatedly, right? Laying bits on top of each other. So basically, this brute force approach, we discussed like four approaches: calculate, parity, then the brute force approach. One time, simple, easy to explain. Minus drop lowest bit, which is okay. Sparse inputs, few ones. Then we have lookup table. But it is used for millions of repeated computations. And then we have XOR folding too, which is log of n. Used for single large words. Is elegant. So what is the patterns? X and 1 basically is the last bit of 1. X shift right, move to the next bit. X and X minus 1. Erase the lowest 1 bit. Result here between 0 and 1, and then lastly 0xFFF. Keep only the last 16 bits. This is also called masking. So these are the patterns to remember. This is it, friends. This is visually, this is analogy. Discussed 4 approaches and their points and patterns to remember. Okay, I think this is it for this video. I'll discuss more approaches in the upcoming video, but for now, this is the one. I hope you liked it. Thank you for joining.